Good evening, everybody. I welcome everyone to the second seminar class of the Berlin Digital Classicist seminar, which is today presented by Jiménez-Badillo, who's coming from Mexico, so he's our most traveled person in this series. We're very happy to have you here.
Thank you.
And to give some insights about your work you've been doing across the big sea.
Yes.
He is working and living in Mexico, Mexico City, and is member of the National Institute of Anthropology and History. And he has both a very strong background in anthropology and archaeology in terms of studies and practical experiences, but also a background on computer science and computer applications. So he has both degrees in both fields actually.
Yeah.
Some of them made or done in schools and universities in Mexico, but also a PhD at the University College in London in the engineering department, the field of geomatics, where he already tackles, as I see it, some research interests which he's going to present here, talking about recognition of spatial networks, spatial matters, spatial patterns in 3 dimensions, which is direct leading to the topic you're talking today, analyzing formal features of archaeological artifacts through the application of spectral clustering. Before you start, just two more formal words. I pass around the attendance list where you please sign in, and if you have not done so far yet, enter your email so you get a member of the email list which Matteo has set up to keep you informed about new events, changes and so on. And if anyone else needs a WLAN account, I have the password details. If everyone needs this, I can just share this as well. For the further proceeding of the evening, Mr. Diego Jiménez-Badillo is talking. We are going to record this talk again and then have a sort of official discussion which is going to be recorded as well and put online afterwards. So if you have some really harsh and critical words, keep them for the private bit afterwards when you have some wine, which is not recorded anymore. So just to keep you informed that part of the discussion is also recorded and made public for the others out there in the net. Yes. So thank you very much again, and you have the words.
Well, thank you very much for being here. This presentation is actually part of a much bigger project that deals with analyzing features in archaeological artifacts with the idea of approach and automatic classification, which is, as you know, a very basic task in archaeology. So the project actually includes not only the application of clustering techniques for unsupervised learning, but also acquisition and analysis of 3D data, 3D digital models, the application of computer vision algorithms for automatic recognition of artifacts, and finally, our final goal is to reach an automatic classification of shape features. That would be our last part of the project. I will present it today, the clustering algorithm that we are using, and hopefully I will have some time to show you some of the, not only some of the 3D digital models that we have extracted, but also some of the computer vision algorithms that are using to analyze archaeological artifacts. So hopefully I have chance to show you some of the software that we are developing. But the presentation is actually focused on the clustering algorithm because this doesn't need any 3D or any special techniques, but it's a very, very powerful tool to classify categorical data in archaeology. So hopefully you will find it useful, and if you are interested, we can share the software, or we can probably in the future try to help you analyze your own data. With this, we produce a software also for the spectral clustering. The spectral clustering was born in the field of speech recognition. Speech is described as a wave, you know, and so they have a very hard task trying to separate words and trying to separate and recognize different levels of speech. So in that field, they developed this technique, which is quite clever, actually. It has a lot of mathematical tools. So we discovered that this was a very useful technique for that, and believe in applying it to archaeology, especially for using categorical data. So our contribution is actually bringing the technique from the field of speech recognition to archaeology, and hopefully you will find it useful. As a study case, we choose a collection of masks from the Great Temple of Tenochtitlan. The Great Temple of Tenochtitlan was the main ceremonial center of the Aztecs, and the remains of this center are located right in the middle of Mexico City. You will see here two pictures. On the left, you see these are the remains. You can see the mouse, right? Yeah. So you see here the remains of that side, and you can see a reconstruction, a virtual reconstruction here, which you can see it's a very big temple. It's like 60 meters square each side of the pyramid. And in these platforms around this, we have found around 200 offerings. Some of those offerings can have as little as 30 or 40 objects, or as many as 2,000 or 3,000 objects. So it's a huge variety, both in the quantity and quality of the offerings. This is a reconstruction of how the ceremonial center used to look. And this is done according to historic sources. So it's pretty much what we know about that area. So what is important about these artifacts is that we focus on a collection, a small collection of these artifacts. And the important thing is that these are very schematic features in these stone masks. You see this, for example, this is a very geometric, very schematic, whereas this is a typical Aztec masks, which is more naturalistic, right? And these are more schematic. So you will see that this has attracted the attention of many specialists. First, because the masks were found in a post-classic context. Post-classic meaning 1390 to 1469. That's the chronology of the offerings where we found these artifacts, these called Mezcala masks. And the second intriguing thing of these masks is that they don't resemble anything Aztec, like this mask, but they are much more similar or almost identical to masks and figurines that come from the state of Guerrero in southern Mexico. Guerrero is about 300 kilometers away from the Aztec capital. So it's two intriguing problems. One is the chronology, where we found these masks, and also the location where they are supposed to come from, right? The location is not so much difficult to explain because the Aztecs used to extract tribute from conquered towns and also used to trade objects from very long distances. So that would be difficult to explain. But together, the problem of the chronology, being found in these artifacts in such a late context, whereas the other masks that we know in Mexico, identical to these, came from 1,000 years before the Aztecs actually came to Mexico. So it's like these two things, why these masks are in a post-classic context, and why they come from this Guerrero style features. So that was the motivation for the project, was try to put some order in these questions. So there are a lot of discussions in the last 30, 40 years about how many actual styles are in this collection. And we have to start classifying the formal features of the artifacts, and that's why we started this project. So what we actually want to do is first a clustering, which is the most basic thing. And as you all know, one of the most important applications of clustering in archaeology is unsupervised learning, which that means learning from the collection, not imposing any criteria or how we are going to classify, but it's learning from the collection, trying to find patterning in the data themselves. Once the collection has been segmented, it would be easier to distinguish potential classes in the future. So like any other clustering algorithm, what we need is to separate the masks. We conceptualize each mask as a point, a data point in the clustering algorithm, and we try to separate those points into groups that are homogeneous and separate them and have very, very cohesive groups that actually oppose or are very different from the rest of the groups. So that's the key of any clustering algorithm. So the key to the quality of any algorithm has to be judged on how successful is it to accomplish greater homogeneity within a group and greater heterogeneity between groups. And in archaeology, well, the two most popular approaches are the component linkage algorithms, single and total linkage, which are based on measuring distances between points, how distant are different points from each other, to see how, to locate clusters. The component linkage algorithms are good for elongated clusters. When the data sets are biased in that direction, elongated clusters, they are very good. But they are very sensitive if there are some noise in the data. And the other group of algorithms are the k-means algorithms, which are good for finding rounded clusters, but not for elongated clusters. So both techniques are good in some respects, but still have some problems for variety of different types of clusters. Well, some years ago, like in 1986, two researchers in Mexico analyzed the mask collection with a numerical taxonomy with total linkage. They define different kinds of for example, of shapes, the mask, the profiles of the mask, or different types of eyebrows, different types of noses. See, they did like a dictionary, and they classified all the 162 masks and 220 figurines. However, and the classification was reasonably good, but still left a lot of problems because there were at least 20 masks left without classification, so like unique pieces. And most of the groups that they defined were not well populated. Like I said, 13 groups only include 2 masks. So this is not really helping to define more groups or to find better groups. So we tried. One of the reasons we also choose this collection as a study case is because it presents all these problems. It's well known. It's important to solve these stylistic problems, the chronology problem, etc. So it's a good study case, but it's not. Our research is not focused on solving only these problems. We want to generate methodologies. That's our main goal in the project, right? So. As we said before, we use spectral clustering. Spectral clustering is derived from graph theory. Spectral graph theory, which is a branch of mathematics, which uses a lot of the analysis of the eigenstructure of a special kind of matrix called Laplacian. The Laplacian matrix, I will see the definition, the mathematical definition later, but we don't really need in this session to go too deep into the mathematics, unless you want, but it's very complex mathematics that you can find in many papers anyway. And the good thing of a spectral clustering is that it can be used with any kind of data, and also including categorical data, which is the kind of data that archaeologists use in many situations. So that's a good point for this technique, right? We will try to prove that spectral clustering is more efficient than total and single linkage and k-means algorithms. So first we'll go to the logic of spectral clustering. Just imagine that you have this data set. What spectral clustering does is not to analyze the location of every single point with respect to the others, but to see the connectedness between in the data set. So for example, we have point 2 and point 3, which are actually closer than point 2 and point 1. However, point 2 belongs to this cluster, right? It's easy to see graphically. So what we want is an algorithm with total linkage or single linkage. Probably we will find that P2 or point 2 will belong to this cluster. So we don't want that. We don't want to find that solution. What we want is to find the solution. This is a cluster and this is another cluster. So what spectral clustering analyzes is not absolute location of the points, but connectedness. And what do I mean about connectedness? Well, there is a lot of points connecting point 1 to point 2. So there is a lot of clustering or grouping of these objects, and that's what spectral clustering is good at in this. So because analyzes connectedness, spectral clustering uses a graph representation of the data set. In this graph, each mask or each artifact is a point or a vertex. And then we calculate the similarity between the different artifacts through a formula. In the case of categorical data, we use a distance measure called Hamming distance, which measures the percentage of non-shared characteristics between the masks. So for example, I have one mask, we are using like around 23 attributes for each mask, like the kind of nose, the kind of eyebrows, the general shape of the mask, the type of mouth, etc. So we compare these 23 attributes for each one of the 162 masks through this Hamming distance and see how many of those characteristics are shared by each one of these 162 masks. And the formula for the Hamming distance is this. We don't have to go through to that. And then we apply the Gaussian function, so we can have a dissimilarity matrix. I'm sorry. So the result of this formula is if two objects are very different, the result will be negative or close to 0. And if there are a lot of shared attributes between masks, then the result will be close to 1. So that's the result of this formula. And we use a parameter called sigma to actually control what's our permissible level of similarity to consider two masks similar. Like if they are, it's like a threshold which allows us to say, up to this level, we will consider these two masks similar. Beyond that level, we will say the masks are dissimilar, and therefore we don't link them in the graph. So that's the purpose of sigma, right? It's a parameter which allows us to control the level of similarity that we want in the collection. Of course, when we use, I'll show you later the software, and you will see it in operation. Well, I'll leave it for later. I think it's better. You will understand better when the software. So once we compute the similarity measures for the whole collection, we draw a link between objects that result similar according to the sigma parameter. So we have a graph like this. So you see a lot of objects connected because they have similar values in their attributes. Okay, so what we need to do is to actually we extract. Once we codify these values of similarity into a matrix, we obtain something which is called the affinity matrix or similarity matrix, like this one. In this matrix is is a square matrix where every square, every cell is, each one of 162 mass, and this is 162 mass. And then we see the similarity, the patterning of similarities appearing in this kind of similarity or affinity matrix, right? So we codify the values of similarity with colors. So once this is done, once we have that matrix codified with colors or with values of similarity, then our problem in this clustering technique is to separate the clusters, to find subgraphs in that data set. So we need to find a partition of the graph. And so the clustering problem becomes a problem of cutting a graph. However, cutting a graph is not, has not a solution in real time. It's what mathematicians call an NP-hard problem. So we need to find an approximation, an approximate solution to that problem. And for that is that we use graph theory. We need to go from these links, which are in this graph, we need to get this. But we need to find which links are actually the weakest links in these connections, right? In this case, it's very easy to see in the graphic, but in the data, obviously we don't know. That's what we want to find out, right? So that is when we use the spectral clustering, and one relaxation or one solution for the approximate solution for this problem is to analyze the eigenstructure of a special kind of matrix called Laplacian. The Laplacian matrix is defined in this way. We have the degree matrix, which contains the connectivity of the graph, the degree of each vertex, which means how many connections are linked to this vertex or each vertex. So that's the degree matrix. And then we have the similarity matrix, the one with the values here. The values of similarity between the whole collection. So is this matrix? The definition is very simple. The Laplacian is equal to the degree matrix minus the similarity matrix. So that's the definition, mathematical definition of the Laplacian matrix. There are proofs, mathematical proofs, why this actually brings the patterning of the data more clearly. It's a transformation that makes the differences between the groups more evident for the computer. And so that's why we use it. If you are interested, I can give you the references, because it's a really very deep mathematical theory that you need there. It takes me a long time to actually understand it myself, but it makes a lot of logic. So, as you well know, eigen means characteristic, own, innate. So what we are trying to do, analyzing the eigenstructure, is to find the patterning in the Laplacian matrix. So by looking at the eigenstructure, we can find the cuts, the best possible cuts for the graph. And as you know, this is the definition for the eigenvalues and eigenvectors. The eigenvalue is associated always with an eigenvector. And this is just the definition, the mathematical definition. So there are as many eigenvalues as eigenvectors. It's always in pairs. So to the whole set of eigenvalues and eigenvector, that is called the spectrum of the graph. And that's what the technique is called spectral clustering, right? Because analyzes all extracts all the eigenvectors and eigenvalues in that matrix. So that's only for, I included this only for you to understand why it's called spectral, right? But you don't have to really learn this to extract the spectrum of the graph, because the algorithms do it for yourself, and we produce a software which does it for you, right? But I wanted for you to understand why it's called spectral clustering, because it's just for information. So I will show you a very basic example. This example is only 3 clusters. So suppose these are 9 masks, 9 archaeological masks, and these masks are described by only 2 attributes. Therefore, this set is in 2 dimensions. Yeah? And so we have this. The first thing we do is to build the matrix, the similarity matrix, applying the formula that I showed you before, the Hamming distance with the Gaussian function. So this is what we saw earlier. So, and we obtain this matrix. We color the matrix with the values of similarity. So obviously, those objects that are closer together, that are more similar, like these 3 groups, are going to be more, are going to have higher degree of similarity, therefore darker color, and also the red ones and the green ones here, okay? So what we are seeing, the interesting thing to see here, is that these 3 vectors, these 3, are exactly the same. The same with these ones, and the same with this one. These 3, and the 3, each group has the same vectors. So that helps us understand that in this matrix, there are some vectors who are dominant, who are really important to learn the structure of the data set. So in this case, there are 3 important vectors, which are this one, which is any one of these could be. Then there is another one, this one. There are 3 types of vectors who are dominant in the structure of the matrix. And those are, loosely speaking, those are equivalent to the eigenvectors of the matrix. So when the spectral clustering algorithm is applied to a collection, what is actually identifying mathematically is these vectors. That's what you are finding with the spectral clustering technique. Graphically, it's very easy to see, right? Like here. But when you have 162 masks for times 23 attributes, the data set is so complex that you cannot see anything graphically. So you need the algorithm. So, but if this is exactly what the algorithm is doing. So in this case, for example, you have the similarity matrix here, and you have this concentration of values here is to these 2 clusters, right? This one cluster here, and the other, the inner ring and the outer ring. And in this case, we will have a matrix with, let's say, 4 major clusters, right? So finally, what the algorithm will do is to project those values using those eigenvectors as the coordinate system, and then reproject the whole data sets into that to see which data are more closer to each one of the axes in this n-dimensional coordinate system. And in this case, because it's only 3 eigenvectors important in the collection, we will have a 3-dimensional coordinate system, and then the data will focus more this one here, and this one here, so we will find the partition of the graph. That's what the technique is about. So it's very easy to, it's very intuitive, but it's very complex to perform, so there are lots of algorithms, well, not a lot, like 4 or 5 algorithms. We implemented one. So I will show you the results using this collection of masks. These are the previous results, the results obtained by component linkage, the traditional technique. We have more or less, this is not very good. These are really, could be similar, but they are very different than these 2 other objects. So it's not really, this is not very good cluster. This is good. Both of these have this kind of ear, and the shape is pretty much the same. And this is really a bad cluster because it has this very triangular shape, again with this. If you see this in 3D, you will see that this is almost a volumetric form. It's like a cylinder, this mask. Whereas here it's very flat and with a very prominent nose. So it's really not, it's clustering groups or that are not really similar. Then we have this, a good cluster, yeah, but it's only 2 objects, and there are many more like this, like including, like this could be a better cluster. So this is hypothetical, but the clustering technique is founding this one, right? So We have so if spectral clustering is good, it should be better than this. So this is one of the clusters found with the spectral clustering. Most of these masks are pretty much the same. Both are with this kind of eyebrows, the nose, the eye, the mouth, the shape, the general shape. This kind of shape, I don't know how to describe it. This kind of this boundary rim that has the mask is in pretty much every mask in this group. So it's actually clustering pretty well. This is another cluster, or you remember this mask, it was in the other group before, now it's in its appropriate cluster. You can see we are in this clustering, we are not considering the raw material, the kind of stone, but you can see there is also a coincidence not only in the shapes or the shape attributes, but also in the kind of stone, which tell us that actually, we learned from this collection that maybe the kind of stone and the manufacture technique has also to do with the style of the mask. So you see here is also another kind of stone, and also pretty much the same artifacts, the same kind of artifacts. So this is another one. Yeah. And this is another one, and it was a very good surprise because recently they found that these masks are actually not from Guerrero, but from Teotihuacan, which is another area of Mexico City. But after we managed to produce this cluster, and this was seen by a specialist in that culture, then he identified, oh, this is a mask that I have pretty similar in other museums, and they started studying, and actually now we think this actually came from Teotihuacan and not from Guerrero. So it's one of the findings that we did with this technique. This is another cluster. You see this kind of shape, the kind of mouth. So pretty much it's helping us to learn about this collection. This is another group, very identifiable group. Even there are two fragments, but it can belong to the same kind of mask. Spectral clustering depends on you to define how many groups you are trying to obtain. So you have to decide beforehand how many groups. So it's an exploratory technique. It won't give you just a clustering magically, but you have to say, well, I'm looking for 20 groups or 30 groups or 10 groups. And besides the level of similarity, which is sigma, you have to know how many groups you expect in your collection. But what we are now experimenting is with algorithms that will allow us to learn how many groups are actually in the collection from the collection itself, without the archaeologists imposing the number of clusters. So that's what we are experimenting now. So it's something that we hope to finish in the next couple of months to see if we manage that. There are algorithms already published about that. We still haven't produced it to distribute because still the interface we are still working on the interface, and you will see it's in Spanish. So we just finished about 4 weeks ago. So, and we were just experimenting. Let me see documents. So you load your data set. You have in this area, you can see each mask with its characteristics, all the attributes, the description of each mask. So you have all this. And then you can do the clustering. In this area, you have the sigma parameter. You see what happens if I put a very low sigma. That means that I want really the objects which are very similar. Well, let's put 0.2. That's objects that are very similar, right? And let's say I want 10 clusters, right? In this side we have the attributes, before we have the objects, all the 162 masks. So here we start seeing, these are the clusters that are, it's going to find a very big cluster and then very unique objects. So like this, it's going to be a lot of single objects which are not very similar to others. So you will find, which in some technique, in some data sets, is not a very good strategy to use very high levels of similarity. We need to be a little more flexible with that. So with let's say we say 4, which still strong similarity, but we open up the number of clusters, you will find more relaxation, more similar things, right? As you can see, the algorithm works very quickly, which is another advantage. The implementation of this algorithm was used with the parallel computing, so it's more, it's very robust and it's also very quick. So you can have very big data sets and it won't be a problem for the program. You see here is identifying these 2 fragments. So what you can do with software is actually explore a collection. Is try to see, you learn, I learn a lot about the collection. Even if I knew the collection very well, I learned because suddenly you have 2 pictures of 2 masks that you won't consider before, and you start seeing, oh yeah, this is similar because da da da. So it's quite good as an exploratory tool. Example. This is also. So this is. Then you have another function here. You can see this mask to which is related in this part of the software, right? So it helps you to know the collection much better. And then I finally, well, this is the clustering part of our project, but I also would like to have some time to show you the 3D work that we are doing. This is a project. This is the second part of the project, which is we intend that the machine compares and retrieves artifacts that are similar. So imagine that you have a 3D model of an archaeological artifact, and you want to compare it in the web to hundreds of other objects that are on the web. In this case, we have it in a repository, in our repository of the collection in the museum I work for. So that's the project. This part of the project is matching and retrieving archaeological artifacts automatically. So we develop a recognition system for shapes, 3D shapes. So imagine you have one query model, like this one. You have this model. Imagine you find this, and you want to find similar artifacts. So what we have implemented is 3 algorithms. One, the first one is this one, the distance algorithm. What it does is to describe that artifact, this artifact, measuring distances through millions of points randomly between 2 points, distance between 2 points. Another descriptor is distance, is the area of the triangles in the mesh that produces this archaeological model. Another one is the tetrahedra, the volume of the tetrahedra. And the last one is the angle between the vectors that compose the mesh. So it's like 5 measures and it's histograms. But we found, that was our first experiment, is easier to implement. So we started with that. But we found that it was not really very robust. It's not really very good. I'll show you why not. You will show. So right now, what it's doing with the query model, I have that model. That is our query model. Is describing in terms of these descriptors. And the next step is compare those descriptors with the descriptors in the whole collection of artifacts. We have like 500 artifacts for this experiment. But you will see it's not this first algorithm is not really very robust. We left it there just to show the differences because we have found better techniques. So as you can see, it's not too slow. But if you implement this through the internet, it becomes really quite challenging. So that's one of the technical problems we are having to deliver the data. The analysis is not, because as you see, it's finding quickly, but the delivery of the data through the web, because it's delivering all these models. So you see that is sending objects that are not really quite similar, right? So this it was not a good experiment. We found this one much better. In this case, the second descriptor uses the symmetry, different axes of symmetry, slices the object into, in this case, we are using 32 slices in different angles and analyzes the symmetry in the shape. This is the descriptor. This is the representation of the values that found, and this is the comparison. So we've been doing experiments with these different techniques. Now, one very important thing to say about this work so far is that we are only comparing global forms. Global comparison considers the shape of the whole object, as its name implies. But what we need in archaeology is not that. We need to go beyond the global matching to something called partial matching, which is look at the details of the objects. And that's what we are trying to do next year. That's the next step in this project. So far we have only the global part resolved. But not, that's one of the reasons we haven't published the whole work, because it's just half the way. The solution is only half, the global matching, but not the partial matching, which is we are going to start working on that next year. Now it shows all the similar ones, but we have in this collection only 5 artifacts the same. So we need also to find maybe a threshold to say, well, they have to be very, very similar and don't include any more, right? Or include all the others, which are, even if they are not too similar, like in Google, that you find something which are perfect match for your text query, but sometimes you find something which is not really very relevant. So this is much better, as you can see. These artifacts are pretty much the same kind of deity with the position of the arms and everything. So what we want next year is to be able to separate, like for example, this kind of headdress, find objects which has this kind of headdress, or some of the attributes here, which are iconographically important. But we want the machine to do it automatically. That's our challenge. The final challenge would be that, but still difficult. We are still working on that. I'll show you another object. Let me see. One of the masks. We have one of these masks. What we did in the spectral clustering, we are doing it in 3D, which is this. It has to find masks that are pretty much, well, they are very similar. That's the challenge. But this is the description, the mathematical description. So we are now comparing with the collection. We have these results. As you can see, the masks are pretty much similar. One thing we would like to improve in the interface is to be able to rotate these objects, because right now are only snapshots. But that's a solution we found to deliver through the internet, because here it wouldn't be a problem, but through the internet to bring these models back would be very, very time consuming. Not the processing of the algorithm, but just the transmission of data. So we have to compromise on that. We said, well, just snapshots instead of being able to move the object. Because it would be great to see if this object behind is similar or not similar, right? Because right now it's like a picture only. And we want to do this fully 3D. But that's a compromise in terms of performance in with the software. So we have this. We have another object here. It's a pot. This pot. So you can see it's finding really objects similar. And it's comparing the whole collection, right? So it's really cooling up the rest, like the mass and everything are not here. It's only the pots. So the algorithm is working well in terms of general shape, but we need to go to the partial matching. And that would be all. If you want to make any questions or.
Thank you very much. For this very impressive work and
Thank you.
presentation.